Hi, everyone. My name is Joshua Buck. Thank you for joining today's webinar. We'll be discussing how to benchmark AI inferencing at the edge, where we can measure performance and efficiently for real-time deployments using BrainChip Akida's architecture and Edge Impulse. Today, we have with us Todd Nakunj from BrainChip and myself, Josh, from Edge Impulse. And Todd will be doing a presentation, and then throughout a little bit later in presentation, we'll have a live demo of using Akida with Edge Impulse. If you do have any questions, please use the Q&A feature of the Zoom chat. We'll be looking at those and then we'll be addressing them as they come up. We'll also have a Q&A session near the end of the presentation as well. Thank you for joining. Todd, go ahead, share screen.
Hello, everyone. Welcome to the BrainChip Edge Impulse webinar today. Today, we'll be talking about how our IP makes your IC smart. And I'm Todd Vieira, the Director of Customer Engagements, and we're here with Nakunj Kotecha, who's our Solutions Architect. With that, let me tell you a little bit about BrainChip. We are the leading provider of IP into a variety of the AI ML spaces. We have 15 plus years of AI experience in research and development and implementation. And we're really the first to commercialize our AI IP in the neuromorphic approach that we're providing today. And we're a worldwide leader of AI processing, and we have centers of excellence in the US, Australia, India, and France. And a couple of our major customers that have licensed our IP are Megachips and Renesas. And we have a variety of other customers such as NASA, Mercedes, and Valeo, and many more. You can look on our press releases for various other ones. So last year we announced at CES, Mercedes-Benz utilized our IP or our chipsets in their EQXX concept car. What they're trying to do is get over 1,000 kilometers on our charge. And we were the in-cabin solution that they found that was 5 to 10x more power efficient than traditional AI solutions today. And with this year, what we've talked about is our second generation from perception to cognition. And with various quotes from various companies, one being Roger Wilkinson, of how our technology is really enabling them to look into the future and drive solutions that are going to be beneficial in this approach as we move forward for next generation AI. So let's take a look at some of those key markets we're doing. We're actually on the edge where we're looking at industrial and automotive, where efficiency and power optimizations are very critical to the battery life of some of these components. We're looking at health and wellness with our next generation technology to do vital sign predictions, sensory augmentation, and fitness and training. And then there's a whole host of home consumer applications that are applicable to Akida's technology for AI inferencing. So let's take a look at some of our features compared to traditional deep learning accelerators. First of all, most traditional DLAs, whether they're CPUs, GPUs, or TPUs, they do matrix multiplication and computations of all the parameters that they have to do compute on. We do convolutions in the event domain. Now, what does this mean? This means that when you have an activation map and you're doing your matrix multiplications, about 50% of those values are 0. And because we do smart computation, anything multiplied by 0 is going to be 0 by default. So we do not do computations on those values, therefore reducing the computations needed to get to the same answer compared to a traditional DLA, which reduces your overall power. And because of this, we are fully utilizing the activation and weight sparsity. A lot of times, some of the deep learning accelerators prune your filters and kernels. And we not only do that, but as I said, we fully utilize activation sparsity, where a key amount of the total computation is done, therefore reducing the power and increasing your overall efficiency. And then the other thing is we try and work within our neural processing unit, so you don't need your CPU to do the computations on a layer by layer basis. We run that full network without a CPU intervention. So that optimizes your system efficiency, where I use my system's bandwidth for the applications processor and not the neuromorphic computation that we have doing these neural networks of today. And as I said, we have a self-configured DMA. So when I'm building my model, it knows how many computation engines I have, where it's storing those results, and utilizing it without intervention from the CPU. So this increases your system's efficiency. And then another unique feature is we have at-compute memory. So each one of our MPU engines has at-computation memory, and this reduces your bus traffic and minimizes the overall latency, so I can get a quicker, faster responses for my neural networks that I'm running on my SoC. And then with our event-based processor, we have special characteristics that we can do on-chip learning without retraining on the edge. You don't have to go back, rebuild your model. I can do what we call device personalization on the hardware, so I can add new classifications on the edge real time without any interaction from the cloud or that connectivity that may be needed from a traditional DLA. So let's take a look at some of the types of neural networks that we support. Really, it's about vision, audio, olfactory, gustatory, or any type of sensor. We take any of those networks in. We use our MetaTF software development kits to build a model that runs a self-managed neural processing unit that supports any network and complex operations. And I want to reiterate, without the CPU. So we can operate in standalone, or we can actually use the host CPU integrated into the SoC to have a extremely efficient design and bring those neuromorphic efficiencies to the traditional models out there in a simple, elegant way. So here I have a couple of demonstrations that I'm going to do with FOMO, our faster objects, more objects. So when I hit play here, we have a turntable that's running, and I have an object detection model that is tracking Skittles as they come in. So you see how these Skittles are going around the turntable, and it's identifying those. And as I throw more Skittles in, it's actually looking, determining what those Skittles are, where those Skittles are, and tracking it with those blue dots. And it doesn't matter, I can have 2, 20, however many, multiple objects that it's tracking real-time live at 0.75 millijoules per inference. Now, furthermore, I have another demo on the right-hand side here. And what I'm doing is I have the same turntable, but I have several objects like the Kit Kat, I think there's a Reese's cup and a Bolt, that those are not being looked at. I just threw in another candy bar, not tracking that. And you can see how it's only tracking the Skittles. So as the Skittles are going around, you have the blue dot on there that's tracking those objects, and you're able to do inferencing real time at about 18 milliseconds per inference. So these are really nice little models that allow you to do multiple object detections with the Akida neuromorphic solution. Oh, yeah. So next, I have another object detection algorithm. And what we're going to do here is I have nuts and bolts. And this is with the DVS camera. So this is an event-based camera from Prophecy. And as I show it running here, I've actually had to slow the video down so you can actually see it. There's a lot of motion blur when you're doing a DVS camera, but we're able to slow it down so you can actually see what's going on. And I'm counting these nuts and bolts objects as they pass through. So this is a little bit more complex demonstration, where as each one of these individual components are dropping down, we're identifying which component it is, put a bounding box around that component, whether it's a nut or a bolt, identifying it and counting it. So you can see the count on the left-hand side. It goes from 0 to 5 different units in there. And this is really nice for counting high-speed objects in real-world industrial environment. So on this next slide, I'm actually not only counting those, but I'm actually classifying the nuts and bolts. So as you can see, I have one nut that goes down and 4 different bolts that it counts those real time at real time. So with our Akida BrainChip model development software platform, we have a couple different ways to bring your models into our environment. We work with people like Edge Impulse who can develop and deploy with no code needed. If you have limited expertise, nice menu driven, they've integrated our process and our SDK within their development approach. And Josh will talk a little bit about this afterwards. He will actually run through a demo as well. And then for those of you who have a little bit more expertise in developing models, we actually have the BrainChip MetaTF that is a backbone that is integrated in Edge Impulse, and you can actually run that standalone that's built on a TensorFlow Keras model optimized environment. And we are planning on supporting PyTorch and Onyx models later on in the year. And then we also have third-party software applications partners like Inviso and Emotion 3D that you may want to have your application software and model development that we work with to run on our hardware as well. From there, we generate these models that can solve these applications programs with the model binary, and then that model binary will actually get implemented and with our runtime library deployed on the hardware that you designed for your SoC. So from concept to delivery, we have our MetaTF and our Model Zoo. Our Model Zoo has various starting points, whether you're doing object detection, you're doing classification, audio, or preventative maintenance models. It'll allow you to transfer learn on some of the data sets that you have and evaluate Akida IP. We have our hardware design with our AKD 1000 chip integrated into a couple different platforms, whether it's PC based or Raspberry Pi ARM based. We're agnostic to the host implementation that you have. It'll allow you to build models, get some sample latency, timing, power numbers. And then we use MetaTF and Edge Impulse to develop our own custom models for our targets that we're trying to deploy and build our SoC for. And then we scale to the particular technology and foundry and process that you're trying to deploy an SoC in. So very nicely coupled tile-based approach. So we are very accurate in getting our numbers from our design product that you may want to do a proof of concept or build some nice demonstrations to see how it works. And then you can develop and deploy those on the foundry and process that you're targeting for your SoC. And with that, I'm going to hand it over to you, Josh, and he'll go over the ML solutions.
Great. Thank you, Todd. Today, I'm going to be showing off how to use Edge Impulse with the BrainChip AKD 1000 system. I work with Edge Impulse. I'm a solution engineer, and our job here at Edge Impulse is to try to get models into real devices, right? We put ML into real devices. I'll be happy to take over the slides, Todd, from here and do a live demo. So let me share the screen. I'll have to take control of the screen, Todd.
Okay.
Yeah. Great. Yeah. So Edge Impulse is the world's kind of first truly integrated ML platform. And we mean that to say that if you've done ML development in the past, you had to have a lot of different tools to connect together, right? You had to, have a tool for managing your data sets. Then you obviously have the ML pipeline itself. And then finally, you have to worry about trying to get it to deploy onto a device. Compiling models and running on a computer is great. To run them on a edge device like a microcontroller or something less powerful than Raspberry Pi, a small processor, it takes a little bit of effort. And then working with BrainChip, while MetaTF is extremely easy to use and things like that, we wanted to make it even simpler, right? To have these kind of no-code deployment options. Our business model for Edge Impulse is royalty-free, right? It's your IP. It stays there. There's no deployment licenses for when you develop models, right? You can take the model and run, and everything is open source behind the scenes. So while we may have a graphical interface, right, the code that is generated is yours and yours to keep. We have 65,000 developers on the platform, over 150,000 projects, and that's always growing. We have a number of enterprises been using Edge Impulse for their model development, like Aura Ring, NoWatch. These are in the health wearable spaces, Ecolab, Bosch, and others for machine health applications, things like that. We work closely with a lot of silicon partners like BrainChip, Texas Instruments, and others to make model compilation and deployment easier. Today, we'll definitely be focusing on the BrainChip aspect of that. And as I said earlier, we have basically two tiers of development in terms of business model. We have a free tier, our development community. That's just need an email address and your name to sign up. You have basically access to the full Edge Impulse Studio tools. We only just limit on compute time and the amount of data that you would have in a project. If you're doing something a little bit more serious and needs extra support, extra help, more data storage, higher compute time, better compute ability, that's when you would move over to a paid model with Edge Impulse, and that's when you'd contact us. We talk about your needs and make sure that we have a good package for what kind of model development you need. We recently released a bring your own model ability to make it a lot easier if you have a pre-trained model to run on these devices. Your ML tool can be coming from anywhere. You could be storing your data in Google Cloud or Azure or even here at Edge Impulse, and we help you link it to the particular model so you can feed that training and test data sets into your model. And the model can come from TensorFlow, Keras, Onyx, PyTorch, etc. With the active learning of Edge Impulse, our idea here is that we want to be able to take data from the device. So if you have a device that's in situ, let's say it's built into a car or built into some embedded application, you can install or build into your code base the Edge Impulse SDK, and then actually connect it up to Edge Impulse so you can get data from those particular sensors. They can be cameras, accelerometers, microphones, etc. We've done things with radar data. We've done things with time of flight sensors. They're all out there, and we've done it with Edge Impulse. The key here, though, is that we're just trying to get you to market faster, right? To make that process simpler from collecting data in your device and getting it back into a model so you can have a good model for your deployments. Today, we'll be looking at how we use Akida with Edge Impulse, in particular the AKD 1000. We're going to work through this workflow, which is we're going to collect some data from the device. In this case, we're going to do some face detection. I'm going to take some webcam data and get it into Edge Impulse, show you kind of the UI. In model design, we already have a model that we're working with, this case FOMO. It's based on kind of the original FOMO is based on MobileNet. We have ported it over to AkidaNet, so it runs on these spiky neural networks that the AKD 1000 has, the neuromorphic chip. We'll do a bit of testing and seeing how that works, and we'll actually live deploy it on the device, and you'll see it run on device. In order to get it to run, we obviously need a device. The device is the AKD 1000. It's the PCI version of that enablement package, and we'll be using it in conjunction with the Edge Impulse Linux SDK. We won't go into the code. I'll show you where that code can be generated and how that's found. But we'll be showing you kind of the no-code way for deployments. To get started for Edge Impulse, you head over to edgeimpulse.com, and we have a developers tab up here at the top and a project search tool. Here we list all the public projects that people have decided to host and make available for free of use. There's a number of getting started tutorials. They're kind of sorted by the particular sensor, like accelerometer, image data, or even audio. We will look at ones that are built specifically for BrainChip. In this case, I'll look for Akida. And we have a few projects specifically built for BrainChip. And today we'll be looking at FOMO in particular. This is going to be kind of face detection. But that same model had also been shown to, detect other things like Skittles, washers and bolts. We even had ones that were counting bees into a beehive as well. So I'll click on the project. This is the main view and main developer aspect of Edge Impulse. This is Studio. On the left, you see a number of different tabs that a user will click through, or a developer will click through in order to build and get their training set in there, build the model, and then eventually deploy it onto the device. I'll show you how that works by connecting my webcam to Edge Impulse. We have here in the data acquisition a number of images already collected for this project. Normally one would then clone it into their personal space. This happens to be a public project. So I'll go over to the clone project, the one that I have brought into my personal developer account. Same project, now I can actually work with it because that was on a read-only mode before. So now we can actually work with this particular data set. In the data queue, we have the ability to look at the test and training splits, see how things are laid out. You typically want to have like kind of an 80-20, somewhere in that range. And then we can collect live data. So this one was built from this model had already taken in just a kind of preloaded data set, from a couple of web sources, but we can actually connect to the device. So I'll connect to my computer here and it will connect up to my camera. I'll give it permission to access. And there I am, right? So here I'm just going to take a few snapshots of myself. I could probably look better today. And what this is doing is actually uploading data to Edge Impulse. We have this ability to do for webcams on your computer, or even cameras connected to the device, right? So if I had an embedded device with a camera, say like a Raspberry Pi or one of the Sony Dev products, we can take those camera images and upload them as well. What happens when I click on capture here is it's actually uploading the data to the project. So if I come back to the project, you'll see I have a couple of new images that I can work with. They're unlabeled. We don't know what we're trying to detect in those images. So we can come in here and actually edit them, right? FOMO is a object detection, not image classification. So in this case, we're going to actually draw bounding boxes around my face, since we're going to try to detect my face. It's an awesome thing. My name is Face, and we can do it here as well. And then we can go through each one of these on this view, or we can go through the labeling queue. Labeling queue is kind of neat because it will detect kind of movement within the images based upon this label suggestion option up here. And it will help make labeling faster. So I'll save the label here, and then you'll see it kind of grabs the next set without you having to draw bounding boxes per each image. That's really helpful when you have a lot of things you want to label or draw bounding boxes for applications that require it, like that nuts and bolts. You can imagine our Skittles where you throw 20 of them on the screen. Having to go through 100 images and drawing bounding boxes for each one would be quite a tedious task. We try to make that simpler by having this labeling queue and detecting things in that image already. A lot of data sets, take a couple hundred images to have good training. Obviously, you want to be aware of the biases that you build in your set. So don't just have it in one background, one set of screens. Try to vary it out, try to vary the lighting conditions so you have a good breadth of what the camera might experience, so you can have good detections out in the field. The key to Edge Impulse, in the main section that you'll be spending a lot of time in as a developer, will be the impulse design itself. Here, these few blocks describe the process of what it's going to take to get data from a sensor, put it into the model, and then what the model is going to spit out as a feature or an inferencing result. In this particular case, we set up the inferencing to look at the camera and squash the image down to a 160 by 160 pixel image. We will process it as well. The processing is very simple. For this one, we're just going to keep it as an RGB data set. And then what's unique for the BrainChip integration with Edge Impulse is that we have integrated a number of their models as well. So in order to work with BrainChip specific products, you do need to choose the BrainChip Akida learning blocks, and then you'll be able to select the model in a later step. Since I already have a project that's been cloned and generated the features, I don't have to generate new ones because I haven't added new labels and new data. Different labels like, face, screw, washer to this particular data set. So I don't need to generate new features. But what this step here is trying to do is look at the data set, look at the image spaces that we have, and then try to make sure that we process the training to get it ready for, or process the data set to get it ready for training. This view is very helpful because you might be able to see things that you might have mislabeled or stands out different from the rest of the pack. And maybe you want to focus in, and that helps look for biases in your data set or things that might be incorrect before you get to training, right? Lastly, in the impulse design is actually selecting the model. Here we have the ability to grab FOMO from this particular data set, or sorry, for this particular model in Edge Impulse design. And you set up the training parameters that you have for the particular model that you want, right? 60 epochs training cycles takes a few minutes to run. We can go see, after training, the precision score that we have, and then some of the confusion matrix to see, what is it performing well on, what it's not performing well on. What we have here on on-device performance is kind of different for BrainChip because inferencing time and peak RAM usage doesn't really apply for the the RAM usage doesn't really apply for this neuromorphic processor, right? Because we load it onto a device, we're not running the model in RAM, right? We're not running it on the CPU, we're actually running it on the Akida device. I'll show you how that inferencing time looks when we actually run on device. You'll see it, runs very fast for this particular model. If we had kicked off a training session here, you'll see it's going to basically load up in the cloud, get the training data set, and then feed it into the model. It takes about a minute or two to run for this particular set. We can go look at previous job history and kind of see how it's run in the past. So I'm going to load up this job that we've done. This is a training job that we ran just a little while ago. And what we're doing for Edge Impulse is we're taking MetaTF, which is BrainChip's SDK, and then compiling the model so that it runs on that particular device. We can see the different layers of the model if you're interested in that kind of thing. But then we also can see model sparsity, number of MP and nodes that are used for this particular model. So, BrainChip's in the IP business, right? They want to sell IP to different silicon vendors. So if you have a particular model that might need to run on a BrainChip specific IP, this is where you get that kind of information to see what kind of size you may need for this particular model. There's ways to optimize this. So definitely talk to Edge Impulse, talk to BrainChip to see what we could do to help you lessen, the size requirements so that you run the most efficient on your particular design.
Josh, I just want to pause you there. There's a question in the Q&A section. Should I need to specify the kind of neural network and layer depth?
So there's two ways you can do that with Edge Impulse, right? You can choose kind of a pre-built model architecture, in this case, FOMO. So you don't have to necessarily specify the layers. Now, how that looks inside Edge Impulse, you can always go to the Keras expert mode and see how the layering structure is set up and how we change the base of the Akida net model to add a different classification head. So if you want to tweak that, you certainly can. There are certain constraints when you're trying to build for the AKD 1000. There's certain layer requirements and, how you have to set a ReLU after certain things like that, that you can find inside the BrainChip documentation. We do have another project as well that has a lot more models. This one's an image classifier. So we already have a ton of BrainChip models that you can transfer learn that you don't necessarily have to go tweak the layer settings. Hope that answers the person's question. Nakuj, I'm not sure if you had anything you want to add to that.
Yeah, I think just you answered it perfectly. Just one slight thing. As you mentioned about the constraints, right? So With Akida, with moving on with our IP, we work very closely with our customers to make sure that we're able to compile their model and convert them as well. And then we try to integrate a lot of these features onto Edge Impulse. So really, and Akida is a platform where we don't restrict our customers on, hey, you can only run these set of networks. You can choose your own network as well. You don't need to use the networks that's already available in our zoo or on Edge Impulse Zoo. You can create your own network, see how it fits your data set, how it behaves, and then you can go through the compilation tool and make sure it converts onto our platform and start deploying it.
Yeah, there's another question in here that talks about, do you provide a profiling tool to see where the bottlenecks are?
You mean the bottlenecks in a particular model potentially? So profiling tool, yes and no, right? So what we do have is when we try to make it easy to run on device, so you can see how quickly and how well the model is actually going to perform versus just a simulated ability. We are working on integrating Eon Tuner. We do this for other products as well. We're working for this for BrainChip. What Eon Tuner will give you the ability to kind of tweak different layers of the model so that you can make an engineering trade-off, so to say, for latency or RAM or ROM, which doesn't necessarily apply for BrainChip, but we can do it for maybe number of MPs and things like that. But in terms of seeing where to bottleneck in a particular layer of the model and things like that, I think Nikunj, I forget if MetaTF has that kind of ability at that low level. Yeah.
Yes. So being that granular, right? So MetaTF will be able to suggest what's wrong with your network or how to possibly fix the network if something is going on. And there's also tools to profile the network, so you can get sparsity, as you see in this log, right? You can get a lot more information at the low level that some of you might require. So you can get information such as how many clock cycles did it take. Because it's all IP, such kind of information is important because everyone uses a different configuration of the IP, or maybe they're using a different process node, right? So you can really get more information. In this, we are just trying to log what's the sparsity, what's the NP number of nodes, some basic information. And if you really want to go granular, the MetaTF has the ability to give you those granular details as well.
Mm-hmm.
Great question.
Yeah. Any other questions?
Yeah, and inside the log report, it also shows you how many MPs are used per layer. So you can check that out as well. So if you're looking at number of MPs per layer, it's actually specifying it there, and you have the capabilities to manage that as well. Great, thanks, Josh.
Mm-hmm.
Okay.
No problem. So let's see how our training's coming along. We're about at 40 epochs right now, so we'll let that kind of go through it. I'll just talk about one or two other features of Studio, and then we'll actually do the demo on the device. Of course, while it's training, it's saying I'm not fully trained, so I shouldn't be able to do the live classification. The eventual output that we want to get to for a particular model is to see actually how it's going to run on device. So we have two ways to do it. One is we can connect to the edge device and send data from the edge device back to the cloud. So in other words, we're not running the model on the device, running on the cloud. This is very helpful to see how it's going to, kind of how the ideal case would be, right? For this particular one, I'm not going to set it up and run. But what I want to also show is eventually getting it back onto the device to do inferencing. We have two deployment options. One of which has kind of a subset, and then there's the pre-built binary. The first deployment option is to create a library. In this case, you would click on BrainChip MetaTF model and click on build down here. And what that will do is kick off a compilation so that we get a zip file that contains BrainChip's proprietary format, the FBZ file for that particular model. That's what runs on the device, right? That gets loaded onto the AKD 1000. And the Edge Impulse SDK comes along as well. That's the inferencing SDK for which you can program and write code against in C++. MetaTF has the Python SDK as well, so you can work through that. And then if you're not in the mood to write code, if you just want to get something running on the device and you have one of the enablement platforms, in this case, I have a computer with the PCIe chip that has the AKD 1000, you can select the AKD 1000 as an option to deploy. In this case, I have an x86 machine with that device and build. And what this will do is give you what we call .eim file. And that's really a binary from which you can use the Edge Impulse Linux tools. There's a set of command line tools to run on the device. So I'm going to do that now. I have a device, another computer sitting next to me with the BrainChip PCIe card added onto it, and I have a webcam connected to that machine. I'm remoted into this machine. I have SSH into it, and then for this particular project, I will use this Edge Impulse Linux runner, and then I make sure I tell the target to force to run on the AKD 1000. These commands are online in our documentation. We describe how to do it. I also specify here the API key, so I don't have to go sort through a big list of projects as well. We'll click on enter and we'll run. And what it's doing is connecting to Edge Impulse, downloading the model, and actually kicking off a build to run on device. So this will just take a minute as well. This is because we have recently trained the model, and so it's picking it up from Edge Impulse. We'll let it run. Oh, creating template failed. Not trained. Oh, I kicked it off too soon. Let's see here. Let's see how the training's coming along. Oh, it's going to take just a few more minutes as well. Nikunj, maybe this would be a good chance for you to run through your slides, and then we'll pick it up with the last little bit of live demo here once the training's done.
Okay, sounds good.
I'll stop sharing my screen and then you can take over.
Awesome. All right, so hello everyone, Nikunj, and I'm a machine learning solutions architect at BrainChip. And I'll be talking to you about our next generation IP, which is really building on top of our fully digital neuromorphic event-based design IP. And it's just adding more and more features to it. So with that, in this slide, I want to focus on 3 core features that will really interest you guys. So one is the running models like ResNet 50. And if you're familiar with ResNet 50, these are models that have skip connections in them. So we have the ability to run these models completely on the neural processor. Now with the previous generation, we were still able to run this, but we required CPU intervention. And as Todd mentioned earlier, we really want to make sure that we can make the system efficient enough. So we now have the ability to uniquely run models like ResNet 50 and models who have skip connections completely on the neural processor. So that way you're really building out extreme, running these complex models with very good efficiencies and not relying much on the system or any CPU. The other cool feature that we have now is spatial temporal convolutions. Now, this is something if you are familiar with, we can apply 3D convolutions and 1D convolutions on this. So now we have the ability to handle 3D information data and as well as 1D information data as well. So naturally, this opens up Akida to various other applications such as video analytics, doing extreme, maybe object detection on high-end use cases, or even object tracking in many use cases, and also working with on the sensor side on various sensors which might be giving you different one-dimensional data. Maybe it's vibration sensors, or maybe it's doing audio classification, right? So now with this has the ability to use such kind of models that can leverage these kind of convolutions and use it purely on the raw data. The nice part about this is you don't need any pre-processing because this can eventually work on your raw data. So now you're really building out, again, coming back to the previous point, on a system efficiency standpoint, where you may not need any external hardware, any DSPs, or any other component that is involved in generating those pre-processing. And then for very high-end use cases, we now have the ability to run vision transformers. So we have really built out specialized units within our technology that can run specific blocks of transformer, such as the encoder blocks. And these are operations that are very unique from conventional CNNs that we see today, or that we'll handle today. So it's very specialized and applicable for specialized use cases that our customers might be looking at, and they running vision transformers at the edge. Next slide, please. So just going over what's inside a node, we are talking about Akida IP, and just want to give you a high level overview of what our architecture is all about. So we reference our architecture in terms of nodes and NPUs. And inside a node, if you see the logical representation, we have NPUs and we have 4 different NPUs. Each of these NPUs also have their own memory. So they are dedicated memory. On AKD 1000, which Josh will eventually run on, it has 100 kilobytes for every NPU. And because it's IP, we work with our customers to really scale the configuration and use standard different custom configuration of this memory. So from sensor-based designs that can range from anywhere from 10 kilobytes to very high-end use cases. Some people are also looking at 200 kilobytes as well. So that really depends on what your use cases are and what your constraints would be at the system level. And within the entire architecture, it's all tile-based, so you can really replicate 1 node, 2 node, 4 node over and over again. And what we have is all these NPU engines run on a single clock implementation. So what it really means is we can run these NPs in parallel, and you can have a communication between them via the mesh network that flows on this entire architecture. And our runtime is able to manage the configuration and make sure each of these NPUs that are allocated can run in respectively and individually throughout the entire network. Next slide, please. So when we look at the Akida platform as one platform, right? So today now, because of these new features as well, we can really address networks to run at this very edge of the sensor, right at the sensor level, or networks, that can range up to networks that are running today at the edge of the cloud, right? Where you really have scaling algorithms done. So really, Akida can be viewed, we view it working alongside our customer, view it as 3 different types of configurations. So one is the Akida E, which is for max efficiency. And these where you're targeting your products to be extremely efficient enough. And these are very small configurations. You require probably low compute, but these are always on type of inferencing. And they also need to be self-managed. You probably don't have any CPUs at the sensors. So because Akida can be self-managed, self-configured, you can really deal with as a control unit and apply to algorithms like detection, classification, occupancy detection, so on and so forth. And then most of our, yeah, go ahead.
And we have a question that says, can we reconfigure the NPU at runtime?
Yes, so depending on what you need, you have one model binary, and you can reconfigure it at runtime. If you want another configuration, you can reconfigure that. You can, and our DMA, which is really self-configuring the IP, you just call API calls to our engine library, and these are C++ API calls, and our DMA will self-configure itself and make sure that it addresses the configuration that you're looking at. That's a great question. The next one is Akida S, which is more of a balanced nature, where typically these might be from anywhere from 2 to 8 nodes, and they require a little bit more compute because they're addressing higher end markets, trying to do more use cases, have maybe sensor fusions in them as well. And when it's sensor fusion, we might require CPU intervention to fuse them to prepare one input. But essentially, these are a little bit more computes where traditionally we'll be doing with and specialized MCUs that have ML capabilities. So now you can replace them with Akida S. And then the last one is the Akida P, which is standing for max performance. And so they require like very large compute, typically going from 8 to 128 nodes. And these may or may not involve vision transformers in them as well. And addressing to very large market, which high-end input resolutions going up to even 4K as well, doing high-end object detection, tracking, open up new applications like segmentation, semantic segmentation, so on and so forth. And this may or may not even require CPU intervention, because eventually you'll be taking maybe 4K, but your networks might be using at 512 or 1024. So you might be using CPU for downsizing and pre-processing on these networks. And just one small thing, even though this is classified here, we work with our customers to making sure that you can take components from Akida S and put it into Akida E as well, and vice versa. And we can even go from 1 node to configuration up to 256 nodes as well. And now when you look at it from an application perspective, the Akida E really can address all the markets that today you're looking to do AI with an MCU, but can also try to address the markets that you have specialized MCUs that have specialized ML components in them. So these are markets that you can probably do with applications such as anomaly detection, keyword spotting, doing low resolution object detection, gesture recognition, so on and so forth. And naturally, when you scale up with Akida S, you open up some of the applications that maybe at the sensor level, but also doing with in specialized units and specialized products. And Akida PE is usually for high-end use cases, as I mentioned, that may require, like today you might be doing it on a GPU using very high-end devices, consuming watts of power as well. So we can really minimize that power consumption up to milliwatts level. So depending on where you guys feel, we can really pick and choose the right level of configuration. And this is one of the benefits of having an IP, right? So you can really customize it for your use case and design it such that you are using this, the building up a system at the max efficient level. Next slide. So I just want to go with, quickly on the holistic view. If you're looking at the Akida IP, it is a fully digital design, so you can really scale it down to different process technology. We're working with customers who are looking at 16 nanometers right to up to 4 nanometers as well. And some of the sensor guys are looking to 28, 22 nanometers as well. It can activate all types of neural networks. So you can do CNNs, which is the main core mesh. I can do a native SNNs, and you can also now do vision transformers, which is the transformer block out there. And if you look at this block, it's the size of a node, right? So really, if you are a hardware guy and you want to understand to activate the vision transformers, you can do it as small as within a 1 node. And if you have more nodes, the performance increases linearly. It's extremely efficient to compute because even with the added new features such as spatial temporal convolutions on the main component that wherever it does convolution, we're doing in an event-based domain, which means we are really reducing the amount of computation we are trying to do and maximizing the efficiency of the entire system. And we can really minimize the system load by adding maybe local memory on the left. For example, if there are networks that have very long range, such as skip connections, or you need data to be saved to be used later, you can use it. You can use the local memory, and so that way you're really doing your computation within the Akida IP and not offloading anything on the CPU or not involving any CPU for an intervention. And all of this configuration, including the transformers, including using the local memory, including the mesh, it's all handled intelligently by a runtime and also managed between different layers within a CPU. And we can support up to 8 bits of weights and activation. So you can even downsize it to 4 bits or 2 bits or 1 bits. This is huge because many of our customers now are shifting from 8 bits to 4 bits and are able to utilize Akida as its whole, keeping the computation same, but leveraging a lot in terms of using lower memory size and getting benefits out of power. Next slide. So this is an example for doing video object detection. For some of you guys who are familiar with event-based sensors, we're using a Prophecy EVK4 sensor. And essentially, this is a data set given by Prophecy that has a series of roads, okay? And if you look at the benchmarks today, the top most performing architecture is Gray Net, which gives you a mean average precision of 43. And this is a accuracy standpoint for object detection. Now, when you apply our architecture, which is temporal even neural networks, that is using the spatial temporal convolutions that I talked about, we get 30% better precision. But when not only that, we do that in very few parameters, almost 50 times lower parameters than the state-of-the-art networks that is published on this data set. And because it's much fewer parameters, there are very few max to do, almost 30x fewer max. And if you see, we are working on a very high input resolution that is on this data set. So we can leverage these spatial temporal convolutions. You can build your own networks that can use this convolution network operations, and can even reduce your parameter size and can have a boost in accuracy and lower your power consumption. Next slide. So now this is working with an RGB type of data set. So this is working on Kiki data set. If you look at some of the standard networks which are built out of Resonance 50, the first one out there, we get an MAP of 57. And if you work with our spatial temporal convolutions that is really utilizing the temporal information, you can get equivalent precision. But now you're doing it again with 50 times fewer parameters, and again 5x times fewer number of computes. And we are able to, we estimate that we can provide real-time performance on like 30 FPS, doing under 75 milliwatts of power consumption. And this is huge now because imagine this is probably going in automotive vehicles where a lot of this assisted driving is being used. And power is one of the major constraints with all the EV vehicles coming out there. This is very important, very attractive in these side of segments as well. Next slide. So we talked about vision and event-based. To some of you guys who are from sensor worlds or working with audio domains or working with maybe headsets or some of those kind of devices, this is also huge for you guys because now we have the ability to process on raw audio directly. So if you look at the left-hand side, if you want to do somewhat like a keyword spotting algorithm, today, many of you guys might be doing generating features. In this case, we're using MFCC. So this transforms one dimension of input into two-dimensional input by generating more features. And then if you have a network such as DSANN, these are again convolution networks as well. So you can you get a certain level of accuracy. You can still run them on Akida. But then when you utilize our spatial temporal convolutions that can really work on temporal information, it can do it directly on a raw audio data. Because networks, we know that neural networks are so efficient, we allow them to generate their own features rather than generating it ourselves. So that way, there are a couple of benefits, right? You get higher boost in accuracy because it's generating its own features as well. And you are also not utilizing any additional hardware, such as a DSP component, or you're not utilizing any CPU as well to pre-process and generate those MFCCs, right? So this is huge in terms of computation. And if you look at the size of these memories, of these networks, they're significantly lower. So you get benefits on memory, and also you're doing fewer number of computes. So if you think of it from a heuristic standpoint, we estimate that you can really consume only under 2 microjoules of energy when you're trying to do apply these kind of networks on these type of use cases. And for some of you guys who are familiar with sensor based, they're really small and they don't go down in process node. They kind of stay at 28, 22 in many cases, but they really want to be very small in energy consumption because they are all battery operated. They want to prolong the life of their products. Next slide. So At BrainChip, we focus very highly on partnerships. So we really are trying to build out our own ecosystem that can help our customers as well. So one of such is Edge Impulse out here, who we are jointly working with. We're making sure that a lot of our developers who are using Edge Impulse widely still have the ability to use Edge Impulse and deploy onto our platform. And they're also working with another enablers such as Emotion 3D and Viso. We're working with Intel and ARM, so we can use their host system. We can use their processors alongside Akida. We're also working with Sci-Fi. To some of you guys who are interested in using VIS5 as your host system, Akida is fully compatible with VIS5 as well. And we have a couple of demos that can show working with VIS5. We're working with many other integrators. And to some of you guys who are students in this webinar, and you are from a particular university, we tie up with a lot of universities and we engage with them. We have our courses with them to teach about neuromorphic, to teach about BrainChip. And we try to talk more about so that we can give them the newest and latest technology available. And so they can really go out there, do their own research, or they try to build out some applications that show the benefits of working with the specialized hardware such as BrainChip. So if you guys are interested in that, please reach out to us and we can work with your university to get something going. Next slide.
The model has been trained, by the way. Thank you, Nikunj, for just taking a few minutes to go over that. I can do the quick demo now if I have a control of the screen.
Sure.
So yeah, during the time Nikunj was talking, it just took a few minutes for the model to finish training. So here, I've added new pictures to the data set and trained it off. You can see again, on the log output, how many MPs are needed, the nodes, and the model sparsity. Our F1 score is 84. Typically, we try to improve that, but that's good enough for demo purposes today. Again, I'll run that command Edge Impulse Linux runner. What that'll do is build the binary and run it on device. And it's already built. What you're seeing here is the output from the Edge Impulse SDK, giving you the location of the centroid of the object. FOMO is a centroid object detection, not a bounding box in particular. But we're also doing inferencing time and power consumption. So here I have the webcam connected to the computer. The model is running on the AKD 1000. It's detecting my face, and it's running pretty fast. Inferencing time less than a millisecond. And then power consumption hovering just a little under 8 milliwatts for this particular IP configuration. That was it for the demo I wanted to get to, but we walked through all of Edge Impulse Studio just to, without writing any code, using a custom data set to run on the device.
Okay, thank you, Josh. We had a few questions on power, but I think they were all answered on the demos. Do you guys have any demos in with the slides on TENS and some of our FOMO builds? Any other questions out there?
There's a couple of questions come through that I can see on the chat. The first one is, when is your next gen going to be available?
So our next generation IP will be available in Q3 this year. We've announced it. We're doing some test and benchmarking, which is some of the numbers that Nikunj just showed you, Q3 this year.
Thank you. And then following on from that, is this IP available for commercialization?
Rob, you want to take that one?
Yeah, so we have a variety of commercial models that are available. For anyone that's interested in learning more about that, feel free to contact us at sales@brainchip.com or contact me directly at rtelson, T-E-L-S-O-N, @brainchip.com.
Thanks, Rob. Another one here. What is your business model and what markets are you currently addressing?
I'll let Rob handle that one as well.
Yeah, so again, when it comes to the business model, contact us directly at sales@brainchip.com. And in regards to the markets that we're addressing, the key areas that we're addressing right now are the consumer space, the industrial applications. We're seeing a lot of uptick into the medical device applications. And as Todd mentioned earlier in his presentation, we've had some success in automotive as well.
Yeah, and we had another question about can Akida architecture support signal processing, functioning, filter, noise reduction, or canceling? Our latest architecture, we have some really good denoising algorithms that we're currently working with several customers. So if you're interested, contact us at BrainChip Sales, and we can discuss those results.
Great. I think that's all the questions that I can see in the chat as well.
Okay, let me do one more screen share. So just a final note, if you have any questions, you can follow up with myself or Nikunj, tvr@brainchip.com, or Nikunj Inkotecha@brainchip.com. We'd like to thank you all for joining. Josh, do you want to say any parting words?
No, thank you very much. The recording webinar will be available, here in the next week or so. And if you have any questions, please reach out to the BrainChip team or Edge Impulse. We'll be more than happy to answer your questions. So thank you everyone for attending, and we'll call it stop for now. Thank you.
Thank you.
Thank you, everyone. Thank you, Josh, for having us.